Great. So just before I start, just a show of hands to see how many people here from a police force in Australia. Okay. Yeah, so there's a bunch of you around here. I think this presentation might be particularly interesting and important for you guys. There's been a lot of hype and a lot of research currently on, I guess, predictive policing. And we're trying to tackle this problem with a sort of like mathematical, sort of like fully probabilistic theory. So I'll go, my slides are going to be a bit technical, but I guess that's good for the audience, and I try to make it, as explanatory as possible. So what I'm going to be covering today is a little bit of a summary background on predictive policing, and then sort of like a fundamentals on why our models are useful, why is quantifying uncertainty and being probabilistic important, how are we building these models over space and time, and then ultimately how is the decision-making algorithm of where to go derived, and basically how we apply to the problem of police patrolling and what we're working on to make this better at the moment, right? So predictive policing, or really, could be defined as uncovering and understanding patterns in criminal activity to optimally allocate resources. This, idea of patrolling at specific areas at specific times of the days dates back to the 1900s when police in Melbourne had these, beats they had to cover in a specific time of the day. They would be at every corner on this map, and depending on the time of the day, they would have a different path they would follow, right? So we're talking about more than 100 years ago, and these practices were already used, and they continue to be at some way or another, right? We're just hoping to make this, in a sense, more rigorous and using the state-of-the-art of statistical learning and computer science, right? So there's been a lot of work in the past where researchers have found that there's, obviously hotspots that change over space and time in a city depending on, a wide variety of factors. There's a lot of work on being able to predict, what is the intensity of crime in a different region. This is one of the most popular papers in this area by these guys who started a company called Predpool, right? Their model of repeated crime is based on sort of like what is called self-exciting point processes. And it's derived from an earthquake model, right, where if you have an earthquake, then there's more likely you'll have an earthquake in the same area. So if you have a crime, then it's more likely to have a crime in that same area. But, it's been proven, and there's a lot of work, actually very recent work, where it's been proven that these sort of like approaches lead to a sort of like over-policing and feedback loops that reinforce the areas you will be policing based on the data that you have, and then you go and get sort of like data from the same area, and then you end up going there because you think there's going to be more crime, and that creates these feedback loops that are sort of like really concerning. So what happens if you assume that your model is right and you don't quantify the uncertainty? Well, you end up having those feedback loops, actually, right? So what we are all about is building models that quantify your certainty about your estimations. And I think that is something crucial across not just decision-making in patrolling, but on any kind of modeling that is done that involves humans particularly. We need to be able to quantify uncertainty. And I'm going to sort of like briefly show you how we do that and why that is important, right? So I always use this quote with my students at uni. It's better to be imprecisely right than precisely wrong, right? So if you're predicting the weather for tomorrow, for example, you want to have not just your expected value of the temperature time, but you can provide an uncertainty, some bounds around that estimation, and that is crucial, right? Why? Because quantification of uncertainty can really drive decisions. It can derive data acquisition, right? If we know we're not certain or the model is not predicting accurately enough a outcome variable, then we might decide to get more data about the phenomena. It can also help us understand risk and do a proper interpretation of the results. So I'll show you sort of like a bit of a diagram of how this works in a one-dimensional example, right? So you usually have a function that you're trying to do regression on. In this case, the ground truth is this green curve. There's some data. So for example, this is the underlying crime intensity that you don't observe, right? And there's some data that is noisy around that variable. So usually what people do when they are working with regression is they try to find one single model, one fit that best represents that data. And the way it's done, you usually assume a parametric form. So you say, I don't know, crime or reoffending or whatever, depends on a set of covariates, and you have some parameters associated to it. And then you maximize the, minimize the error or maximize the likelihood, and you get sort of like one model that best suits the data. Now, what we're arguing is that you need to be probabilistic in the kind of model. That means that you're not just finding one model, but you're finding actually an infinite number of models that represent the same data, and you have uncertainty around your predictions and around the model itself. So there's not just single model, but there's a probability distribution around all models, and you're combining the knowledge from all of them to get your predictions. So this all remounts really back in history to Bayes' theorem. So at the center, all the research that we do really is Bayesian. It doesn't matter if it's for criminology or for geology or in health for predicting cancer, right? The idea is that you want to be able to find a distribution over your model. So remember that theta represents a model, the parameters of a model, and D in this case is the data. So the idea is you combine prior knowledge, right? So the data does not speak by itself, but you can encode in these models prior knowledge about which models would be more, better than others. You combine that with the data, and by calculating this quantity, you can recover a posterior distribution over models, which essentially tells you which models are better than others. Now, this posterior distribution, not only informs the models and inference, but also allows you to derive a predictive distribution. So whatever your quantity that you were modeling is, in this case, let's say y is the number of crimes in an area. By using this, the data and the prior knowledge, right, you can integrate out over all possible models. So remember, I was telling you we're not picking just one, but we have a probability distribution over them. And that gives you, in the end, a predictive distribution that reflects what? Reflects the uncertainty in the data itself, and also reflects the uncertainty because you don't know which one is the correct model, and you have a whole bunch of them. So there's a proper quantification of the uncertainty. Now, as you can see here, right, there's a function with some noisy data, and in this case, by looking at the maximum likelihood, you can find the function that best represents this data. These are called Gaussian processes, and for any quantity of interest, so in this case, let's say we're evaluating what is the predictive value of the function at this point, we have the mean expected value, which is that one, and we have an uncertainty bound around that. So we're predicting how many crimes you would expect to observe at 0.7. Well, it will be between these two sort of like bounds, and that's the expected value of it, right? So the idea is that where you don't have data, where you have lack of data in some way or another, the uncertainty is higher, right? And where you have data, your uncertainty naturally becomes lower. So it's great for really driving your data acquisition process. Now, these Gaussian processes models, right, we've used them in the past to model pollution. So in this case, we've used data from 100 and something stations that measure ozone concentration in the US, and we've used the Gaussian process model, so it's this function, over space and time to be able to predict between these locations that are measured what is the concentration of ozone, and then make decisions on these sort of like spatiotemporal models. These same models, right, are being used for crime as well. So they have, are some of the colleagues, computer scientists as well. So Seth Flaxman, for example, he's got this paper on review for the Journal of American Statistical Association, where he's using this spatiotemporal kernel method. So that's exactly the sort of stuff that I'm describing to you. They define a kernel that relates measurements at different locations and quantifies the uncertainty. So we're doing the exactly same thing. This has been submitted this year, so I guess they got in before us with the model itself, but that's fine because we are, in a sense, using these models to drive decisions, right? So this sort of like validates that the way we've been thinking so far is great. So the model that they use actually won a crime forecasting challenge. So it considers several points in time and all the crimes in space to predict what is your expected value number of crimes and also the uncertainty around that. Okay, so how can you use these models for decision making then? Well, this is a technique called Bayesian optimization that I'll try to summarize. It's a simple algorithm, but the idea, right, simple because it's just one loop. And in the end, what you're trying to do is you want to pick your next sampling location, right? in the case of a generic function, is where should I evaluate my function next to find the optimum? Especially when decisions are costly, you need to be efficient when doing this, right? So the idea is that you have a model of a function, say the crime intensity, and you evaluate an acquisition function that is, depending on the model, tells you where you have to go next. So at every point, at every step, you find the maximum of this acquisition function, which is sort of like the reward of sampling somewhere. And you get an evaluation of the function at that location. So you basically, in the case of predictive policing, for example, you actually go there to get a new observation of how crime is looking at that area. And you gather a new observation, you update your model, and then you maximize your acquisition functions again. That tells you to go to another area, and you keep doing this over and over and over again, right? So Bayesian optimization is starting to be used, you won't believe it, in a very, in a very big and enormous range of different applications. Everything from environmental monitoring, coral reef depletion, and now we're sort of like trying to adapt it and apply to predictive policing, right? So we've used it, for example, with the Department of South Australia on predicting groundwater, right? And which wells would be the most important ones that they would be using based on these spatial models and the decision making. And we've also tried to bring this down from a one, this is the data, right? And the idea is that you make a decision based on an immediate reward. So this first row up there, don't really focus on the equations. I'm just trying to show the complexity actually here of making one decision. The immediate reward is already complex because you need to evaluate all possible outcomes. So when police travel to a location, they don't know exactly what they will be expecting. So you need to integrate out what we call all possible outcomes, all possible function values. But then this is one step look ahead, which is myopic, right? In a sense, is answering the question, where should I go next, without looking at all the future decisions that you can make, right? But as in chess or any other sort of like a strategy game, you move somewhere or you go somewhere because you think, well, where am I going to go after that? And after that, and after that. And then you make your big decision based on that. And that equation there is extremely complicated. During my PhD, I think I spent like 7 months trying to solve it, and I really wasn't able to find a solution for it. So it ends up being that you can approximate that solution. And this framework called partially observable Markov decision processes is essentially what we're using to solve this problem. It allows us to define state and action and transition space to maximize a reward. So I'll quickly sort of like skip actually through these slides because I explained these same methods applied to the predictive policing case, but this is essentially how we solve the problem. So how do we apply then all this theory to policing and predictive policing and police patrolling, right? So we have a map of Sydney. We essentially define a grid where we have all the sort of like crime data. This is just fake data for illustration purposes. And the idea is for each one of these grid areas, we aggregate the number of crimes that we see in a period of space and time. And this is our Y. Now, this Y follows what we call a Poisson distribution, or what is called really a Poisson distribution, with a certain intensity. So the idea is that the intensity of crime changes over space and time. So these are the counts, and the counts follow a Poisson distribution with a certain intensity. Lower intensities give rise to a less number of crimes, and higher intensity gives rise to a higher number of crimes. So the idea now is to model this intensity, which is always positive, and that changes with space and time. So for that, we use a Gaussian process model, which is the one that I just introduced. And the idea is that this Gaussian process model uses data from all the locations combined with the parameters of the model that are unknown to learn, using Bayes' theorem, what is the space of models that best represent the occurrence of crime in that area. We do that using variational inference, but that's just details of the inference method. So what is the most important thing is that for a new area, using everything that we've learned across the patterns over space and time, we can predict what is the intensity of crime, and therefore we can also estimate what are the number of crimes that we should expect to see in that area. This is very crucial because now we have the expected value of the number of crimes, which is what everyone, I guess, is used to reporting, but we also consider the standard deviation around that estimate, which quantifies the uncertainty. Now, crucially, these two values, please remember the mu is the expected value and sigma is how much you know about what's happening in that area. We use those statistics to drive the decision-making process. So let's zoom in into a particular area of Sydney and say, let's start by assuming that the police is in this quadrant here in that small grid box. So we have a decision tree view here on the left and a map view. So at the moment, the police is on that area. It has this belief of the number of crimes that will be occurring in that area and the uncertainty around that. And the idea is that the algorithm builds a tree of decisions to approximate the full solution, right? So let's say, what happens if we move to this area? In this area, there's this other orange expected number of crimes, and this is the uncertainty of the model in that area. So we evaluate a reward. Now, this reward function is what is tuned to balance exploitation, which is the first term. How much do we exploit the expected number of crimes, and how much do we explore the number of crimes, right? So it's a trade-off between exploration and exploitation, and that trade-off is controlled by a parameter kappa in this case. So the idea is that after making this immediate decision without taking it, just thinking, what would happen if I go there, you conduct a simulation of, what would happen if I just, follow my default strategy in the future until a maximum simulation length. You get an accumulated reward, which is all the uncertainties and all the expected crime risks across that path, and you backpropagate that to that immediate decision. Now, the idea is that then you come back and you say, well, what happens if I go to this other area, which is the green area here, right? And then you do the same thing. You evaluate another path, follow that immediate decision, you get the reward, you backpropagate it, you keep that reward, and then you keep doing this again and again, right? So just think of one more. So purple, another area, another sort of like path that you can follow. And then you end up doing this simulation many times and updating the reward, right? So after many, many, many iterations, right, you might end up with something like this, right? Now there's a problem here. Can someone spot which one of the colors is incorrect? I'm just kidding. It's random. It's just for illustration purposes, right? But you can imagine, right, how many decisions are involved in a tree of depth 5. It's around 60,000 decisions at every point in time that you have to make. So it's pretty computationally intensive, right? And what we do is we pick the next immediate decision. So in this case, let's say it's convenient to go to the purple square, just because after you've simulated all what could happen in the future, this is the action that immediately gives you the highest reward. That's called Monte Carlo tree search, and that's how, say, Deep Blue won against the champion in chess. That's how AlphaGo, Google AlphaGo, challenge won to the world champion in this game of AlphaGo, which is like really, really complex. So the idea is that you evaluate all your possible actions, all the possible movements that you can make, and the probabilistic outcomes that you can receive from going there, and choose which one to go, that it could be the most optimal one in this case. Now, the details of how we implemented this is, in a sense, like I would say a trial, a proof of concept of how this works, right? Is we get data from New South Wales Police Force, actually 15 years worth of data for the Central Metropolitan Region. This data was actually, we obviously cannot get access to the exact latitude and longitude, but what we did was get that data and we added some noise to the data so we don't know exactly where the crime is, but we have an idea of the area. So we sort of like simulated data, but based on the actual raw data from the COPS database. Now, the crime type, we use domestic violence-related assaults just because we had to pick something, and this one's one where the interaction of police or the presence of police didn't directly affect the occurrence of crime because we didn't take that into account. We just selected a grid size and the number of, these are the numbers sort of like of possible paths that you can follow given a tree of depth 5. At a certain point in time, this is what the tree would look like. So you can basically, go anywhere, but you decide where to go based on the expected number of crimes that you might see in an area and also the uncertainty around that. So this is a video of, one of the iterations that we run on the program, right, with a specific set of parameters. So you can see on the top here is the ground truth, so where are the hotspots in this case, and on the bottom you can see the police sort of like moving around and making decisions at each point in time. So you can see the police car is exploring first the environment. Transparency means it doesn't know what is going on there, and the color represents the crime intensity that it's observing. So the idea is that you can see the path is sort of like first exploring the environment. Why is it exploring? Because uncertainty is high. So it's first driving the model towards reducing uncertainty. And then when your uncertainty becomes lower, you will end up going to areas where you know that crime is going to be high. So this trade-off between exploration and exploitation allows you to learn from the spatiotemporal phenomena and at the same time exploit your knowledge to be able to go to areas where you know crime will happen. Now, the key thing of this algorithm really is that it allows you to tune the behavior of your decision-making process, right? So given you have some ground truth that I sort of like show you, ground truth as in you know how many crimes are going to be in that area, we sort of like experimented with different levels of this kappa. Kappa was the parameter that tuned exploration and exploitation, right? So if you pick a value of kappa, a very high value of kappa, for example, 50, that means you'll just be concerned about exploration. You don't really care about how many crimes you see in an area. You just want to evenly or maximize the exploration of space, and you would end up with a path across Sydney that looks like that, right? So police is basically just wandering around but trying to maximize the information gain, right? Then you have kappa equal to 2, which would be completely the opposite. You're just driven by your previous knowledge of where crime happened before without quantifying the uncertainty. So for example, this would be equivalent of saying, I don't know how many crime thefts we have in an area over the last week. Okay, that's where we will go this time. So if you go there, then you'll probably find crimes again, and then you sort of like potentially give rise to over-policing problems in that scenario. So you have the two extremes, right? But in the middle, you have a trade-off between both, right? You were exploring, but then at the same time, you're exploiting. So the density of these paths is higher. You know, police will visit more often areas where there's more crime and less often other areas. But it would still explore the space, right? And compared to obviously just moving randomly, well, I guess no one would really do that, but we still need to compare with that baseline. Now, results show that not necessarily you get more crimes by following a particular value of kappa. So for example, by trading exploration and exploitation, you can achieve a better root mean squared error. Root mean squared error being your estimation of crime intensity across space is actually lower if you explore, right? And at the same time, this gives you a good trade-off because you are close or in the same grid when crimes happen. Most of the time for this, I think it was one month simulation, right? And yeah, I guess, you know, there's a lot of discussion that needs to happen really into how do we tune this reward function, how much do we want to explore, and how much do we want to exploit. Now, what are the sort of like strengths and also limitations of the model that I'm presenting to you today? So strengths are, well, it's evidence-based decision-making. So we are really, you know, putting in the best model that is out there so far, that is being used to decide where to drill to find geothermal energy, that is used to drill to decide where there's gold, where we're using the same sort of algorithms, the state-of-the-art, to decide where to go next to find crime. So if evidence-based decision-making that quantifies the uncertainty, that is non-myopic, so every decision that the car makes basically is, you know, not where I'm going to go next, but, you know, looking at a multiple-step look ahead, which, you know, creates this enormous tree of possible decisions that we're evaluating. The idea of trading off exploration and exploitation in a quantitative manner as well allows you to be transparent and decide what is the compromise of one and the other, and that we are also sort of like being able to uncover and do inference on spatial and temporal patterns. So in this area, at a certain time of the day, you would expect to have more or less crime. Now, there's a lot of limitations, and that is the reason why we haven't conducted any randomized controlled trials yet. So ideally, we would have some cars that are running our algorithms and compare what are the response times, how close you are to crimes using our algorithms, or, you know, whatever other technique for patrolling, but we just haven't done that yet. And why is that? Because we have a lot of limitations, really, with our method, right? So it's grid size dependent. We're working all of this, and we actually are well advanced, but this is sort of like what I can present today is that, you know, we have this dependence on the grid size, which should change, you know, over, you know, how densely populated an area is, but we just have a fixed grid size that we're calculating. We're working on models where it's not grid dependent, but it's actually what is called a continuous model. Now, mathematically, that becomes, believe me, really, really complex, but we're sort of like about to actually get to a solution on that. we have one different model per crime type, right? So we are, say, looking at domestic violence. Well, this is where crime happens more or less in domestic violence, but we're not looking at different crime types and looking at their relations between them, which is something that we're also working with in collaboration with the Alan Turing Institute, actually. So there's also the need to have multiple patrolling units. So the video you saw is just one, right? We need to consider the case, what happens when you have multiple of them, when each patrolling unit has a different role, and then how they would interact with each other to maximize coverage, to dispatch units in an optimal way. Then we also do not consider the interaction between police and actual occurrence of crime, which is also something that we have to work on. And we sort of definitely need a computer cluster at the moment to evaluate all the thousands of decisions. And I guess this is also very important that we're not making the distinction of different crime types as if, which ones are reported and which ones are sort of discovered by police, which is very important to understanding the interaction or the effect of certain types of patrolling over different crime types. So yeah, I guess that's all the presentation for today. If any questions? Any questions?
Hi, thank you for the wonderful talk. I just have one quick question. Can you just give more detail on the variational inference? Is it the variational base that you use?
Yes, yes.
So
yes,
did you get a closed form solution?
No, it's not closed form solution. So if it would be closed form solution, we would actually just evaluate the posterior distribution. But there is no closed form distribution because of the double stochasticity of the problem. So we have stochasticity in the first level of the hierarchical model with the Poisson distribution. And we also have a stochasticity because that intensity is a Gaussian process model. So when you have that double stochasticity, you have no closed form solution, and you have two options. One is MCMC, so sampling methods, or variational inference. We use variational inference because it's faster than MCMC. It's an approximation. And basically, variational inference, instead of sampling, what it does, it defines a lower bound with a proposal distribution that you minimize. So it comes from a sampling based approximation method to an optimization one.
Thank you.
Hi, Roman. Wow, that was good. Very interesting. I just have a quick question, but much less technical, about why did you choose the domestic violence as a example of this? Because it seems a very important application, but in terms of finding crime for police, I would think that a property type crime or other types of crime might be. Yeah, well,
initially we chose this crime type mainly because there was no apparent interaction between the presence of police and the occurrence, because most of the incidents occur in residential premises. So because we hadn't taken that interaction into account, this seemed to be the best crime type to choose. But what we're exploring now is actually considering all different crime types and their correlation. So that's very interesting research being conducted at the moment, where we can inform domestic violence, for example, based on other types of assaults, other types of robberies, or other types of crimes that are sort of have higher reported rates, and that can sort of drive the decision-making process in a better way. But yeah, we're not yet finished with that. Does that answer the question? Yeah.
I think we have time for one more question.
Hi. So my question was just about, in terms of the scale that you're able to actually or accurately model. Obviously, I think that's probably what you were referring to with the grid size dependence.
Yes.
So how accurately or how large are we able to actually scale these models to? Would it be a suburb or a city or larger than that?
Honestly, you could go entire New South Wales. We only had data with the central metropolitan region, but you could go really, really big with these grid size models. And what we're working now is not being grid dependent. If you have a continuous model, then you can basically use infinite data, and you essentially learn which ones of these data points are important for your prediction at that area, in a sense, right? And we're sort of moving away from the grid space, because it actually doesn't make any sense to send police to a grid where, I don't know, it's in the middle of a park or in an airport, right? So we are defining, or the domain of the function is now going to be the actual streets. And we are sort of like referring crimes, or sort of like we're assigning the crimes to the closest street in a sense. So therefore, the optimization problem is just on streets, and the kernel function in this case, instead of being defined over space, is defined over the street network itself, which allows you to even better understand distance problems. So for example, right, we looked at our model in terms of grids, and the distance between, say, Watson's Bay and Manly North Head, right, is geographically very short. So, the number of crimes that happen in one area affects the other. But actually, if you need to go from Watson's Bay to Manly, you need to travel for an hour or so, right? So they're really far. So that's why we're trying to move away from the grid-based model to a street network one, where the distances are calculated in that network, and hopefully include travel times and all of that. But yeah.
All right. Thank you very much.